All right, here we've got a 6.7 kilogram mass resting on a 42-degree ramp. Attached to this mass is a rope which travels over a pulley to a hanging mass of unknown value. We're trying to figure out what the value of this hanging mass must be to keep this block on the ramp stationary. In fact, to keep the whole system from moving. So we want the net force to be 0 once again. So the goal is, if we don't want it to move, we want the net force to be 0. Now notice I've color-coded this a little bit. I've already drawn in all the vectors, all the forces that are present. The 6.7 kilogram mass has a force of gravity, which I had labeled Fg1, straight down to the center of the Earth. And because it's resting on an incline, it will experience a squeeze between the surface and the mass, which we call the normal force. And that's this green vector. The normal force is always 90 degrees to the surface. Now there's a rope attached to it. The rope itself is what's holding up this mass. Ropes we call the tension force, so we'll call that Ft. Now there's only one rope, so the tension is the same throughout. So there must be an equal and opposite Ft attached to this mass, connecting the two masses together. So it's holding up the unknown mass. And then pulling down, of course, on the unknown mass is its own force of gravity, which I've called Fg2. Now, so far, the forces that are actually trying to drive the system are these pink ones. They're the ones that are parallel to the motion. If this thing's going to move, it's going to try and go like this up the ramp or like this down. So it's not going to travel in any other direction. It can only go along the ramp or straight down if you're the hanging mass. So the pink vectors are the ones that are driving the system. So the green vector doesn't really have any direct play. It's not causing this thing to accelerate or decelerate because it's perpendicular to the motion. However, this yellow one is at a funny angle, and it will have components that are both parallel to the motion and perpendicular to the motion. Now I'm going to make parallel to the motion because that's what's important, pink. So this Fg1 will have a component that's parallel, so parallel to this surface, like this, which I'll call Fg1x. And it'll also have a perpendicular component, which I'll do in green, like this. That's the goal with components, to get the components that are both parallel and perpendicular. I'll call this Fg1y. Now, just as a point of interest, it's not moving this object in that direction, in the perpendicular direction, right? This box is confined to the ramp. It's not going to move in the perpendicular direction. So that simply means that the normal force and Fg1 are equal and opposite. They're canceling each other off. So really, all that's left to drive the system are those pink vectors. So we want to add them all up, and we don't want it to move. We want it to add to 0. So we want the sum of those pink forces, the ones that are parallel to the motion, to add to 0. So this one will say, because it's going down the ramp, we'll say that direction is negative, because we don't really know which way this thing's trying to go. So down the ramp we're going to say is negative. As long as we're consistent, we're good. Up the ramp is positive. So the first tension right here is positive, and this one will be negative. It's going against that direction. And then Fg2 is going clockwise, so that would be positive. And that all equals 0. So again, the tensions, when you look at the whole system, cancel. So we've got a pretty simple equation. We've got an equation that says, when I solve it, Fg2 has to equal Fg1x, the x component of Fg1. Now, let's keep going. Fg2, well, what's the formula? Well, it's unknown mass times g. So that's the mass we're trying to figure out. Fg1x, how do I figure that out? Well, if this angle down here is 42 degrees, you can see I've got a little triangle right in here. So if that's 90, we can easily get this angle. And then turns out if you do your geometry, because you got another 90-degree triangle here, you get a 42-degree angle right in there. So if I look at this little triangle with the yellow, the pink, and the green, Fg1 is the hypotenuse, and Fg1x is the opposite side. So if I write a quick little formula there, I get sine 42 is opposite over hypotenuse. So this is going to be equal to, FG1x is going to be equal to FG1 sine 42. Now FG1 is 6.7, we know the mass, times G times sine 42. So let's plug that in up here. 6.7 times G times sine 42. Now notice there's a G on both sides, so they actually cancel, which is interesting. That means that no matter what we get for our answer here for M, it'll work on any planet. G has no effect. As long as the angle's the same, it'll be the same answer. So when I work this through, my unknown mass will be 6.7 sine 42 degrees, which is 4.48 kilograms, or to 2 sig figs, 4.5 kilograms. So if this mass right here is 4.5 kilograms, the system is in equilibrium and does not move.